Hi, today I'm going to talk about the solutions for the 2025 January contest Silver Problem 1 Cow Checkups. And for this problem, basically there's n cows standing in a line and they all have a species which is an integer from 1 to n. And they're going through a checkup at a hospital, and then the cows will only be checked if the ith cow in the line has a species of bi, which is another array with species from integers 1 to n. And then, so Farmer John has the operation to select two integers L and R and reverse all the cows in the range L to R. And we want to find, for all the possible operations, we want to find the sum of the number of cows that are checked in all these operations. So for example, in this input, originally there's no cows that can be checked. So if the operations are L and R are equal, then these three operations will result in no cows being checked. And however, these operations will all result in one cow being checked. So the sum of these together is 3. The brute force approach to this problem would be to try all the possible operations and then check how many cows will be checked for each operation, and then sum them up. However, this would take too long since we can't try all operations since this would take n squared time. And then, so we can try another approach, which is we can calculate the contribution of each pair separately. So we can calculate the contribution of some index in A matched to some index in B, and then count how many operations would allow them to be moved to the same position. And so we can, since only the same number would allow a cow to be checked, we can keep track of a vector which maps the cow species number to a vector of indexes where those numbers appear separately for arrays A and array B. And then we can loop through all the indexes in A and B and count how many operations that can flip them to the same position. So for example, if we look at sample input 1, if we're currently looking at the number 1, then in array A, the index stored would be here, and in array B, the index stored would be here. And we can, when we loop through these indexes, we would check how many flips would bring these two positions together. So in this case, the only possible flip would be L equals to 1 and then R equals to 3, which would flip this and bring the 1 over here. And again, we can do so for the pairs, the numbers 2 and 2 and the numbers 3 and 3, and count the contribution of each pair separately and then add them to the answer. And again, we can do this for the second sample input. And in this case, since the numbers are already equal, for 1, 1, they're already at the same place, we can count the number of operations that would make them remain at the same place. So any operation that does not move this location would allow this to add 1 to the answer. And so if L and R are chosen in this range only, then this will not affect the answer. And again, if there are some more numbers in the front, so for example, there may be some numbers here, and if L and R are just chosen in this range, then this will also not move this position. So this position would still contribute 1 to the answer. And there's another case where the flips only mirror the numbers around L and R, around this current position, and then so this still would not move the number here. So for example, any operation that flips it here or here or here will just mirror these numbers, so this number would still remain the same. So we realized that we can loop through the indexes that we stored in A and B, and then for the case when AI is equal to BI, then we can count the operations when L and R are both greater than AI. And this is the case when the flips are just here. So the flip only moves numbers around in this region, so it wouldn't affect this number. And then similarly, there's also when they're both less than AI. So greater than or less than AI. And then the second operation if the operation mirrors numbers around AI. And then what I mean by this is that what I mentioned for this case when the numbers only flip around AI but then don't move this number. And what I mean by AI and BI is just the indexes of the number in the first array and the second array. So the index for this number would be AI and the index for this number would be BI. And so for the case when the numbers are not equal, as we already saw here, these numbers, they're not in the same position. And so flips that would make them become in the same position are these, where L is 1 and R is 3. So if there are more numbers, here, then another operation could be that one that flips numbers in this entire range, and the numbers would flip like this. And in this case, this one would still go to this position. And let's look at the sample input 3. and we can look at the one if AI is here and BI is here. Then this is the case where AI is not equal to BI, and the operation would be this one, or this one, or this one. And it would all flip these two numbers together. And so we can count the number of operations, and we realize that it's limited by, so in this case, this one is the limit because the right end is already at the end of the array. And however, if we choose numbers here and here, then the left end would be the limiting one that limits the number of operations. So we find that the minimum distance from the right or from the left would be the limiting number of operations. So in this case, the number of operations would be the minimum distance to the left or right. And this solution is sufficient to pass cases up to number 10. However, there will be issues when we realize that in cases from 10 to 15, the numbers are all generated in either 1 or 2. So if the numbers have a lot of repeats, then this would result in O n² time. And however, we can solve this by binary search, because if we further optimize this approach, then we realize that if we take a look at an example, if AI is in this position, then numbers in this range will all be limited by this index, and numbers in this range will be limited by this index, so the BI index, and numbers in this range will also be limited by the BI index but to the right end. So we can separate this into these regions and calculate the numbers for these regions together. So we can do binary search to find the indexes at these positions. So we can use lower bound to find the index at this position, and then use lower bound to find indexes at these positions and these positions. And then this will allow us to calculate the contribution in this range by using this range would be AI times the times the number of ones in this region. So in this case, in this example, it would be 3, and it would depend on individual cases, and we can calculate it using, because we have the lower bound numbers here and here, we can calculate the numbers in this range using the lower bound. And then this part, the contribution for this pink region will be calculated using this product, and then the contribution for this region can be calculated using prefix sum. So this is because the contribution for this region is limited by the index bi to the right endpoint. So the contribution, the number of operations in this region, if we want to flip this number to this number, would be up to here. And so the number of operations is this distance and this distance, which we can calculate using a prefix sum if we sum all these indexes for bi up and then do n plus 1 times the number of ones subtracted by the sum of bi in the region. So this calculates the index of the sum of these numbers to the end. And we can also do this for these numbers, which is use a prefix sum, just like how we did in the end. And similarly, if AI is in this position, then this will also split into these regions where these two can be calculated with prefix sum, and this one can be calculated with a multiplication. This time it will be n plus 1 minus ai, because it would be limited by this point to the right endpoint, and then times the number of ones. And I mean the number of ones, but then it can be any other number that we're calculating at that point. So, and in this case, I marked the numbers as x. The number x are just other numbers that are not ones, because in these examples I used the number 1 as an example. And now let's look at the code. So let's first look at the code. If we do the approach that I first mentioned, but wouldn't work for cases after test case 10. So for this, we can use a map to store the index in A and the index in B, which correspond to the number. So we can map the number to a vector of indexes in both cases. And then for each number, we can loop through the pairs of indexes and count the number of flips that would make them flip to the same position. So if the case when ai is equal to bi, this is the operation when that position is just mirrored. So if the flip only mirrors numbers around that position, then this is the number of operations. And these are operations when the number is just chosen on the left and on the right. And these are operations when ai is not equal to bi, so it's limited by the distance from the left or the distance to the right. And now, when we modify the approach, we realize that these loops are the ones that are contributing to a high time complexity when there's a lot of repeats. So we can modify that part and then keep the counts for the case when AI is equal to BI the same. But one thing to notice is that we don't need to count this position when we do it in this method, because the case when the numbers are mirrored is counted here. And so this is the prefix sum that I mentioned. So we can do a prefix sum of the indexes in B. And then for these, this is the part where I mentioned about separating it into different segments. So we can calculate the first segment using a prefix sum, the middle sections using a product to time the number of numbers with the number of operations. So, and then afterwards, this part is the right segment where it's limited by the B index. So we can calculate this using prefix sum. And thanks for listening.